Hello everyone. So previously we had discussed on the topic Kruskal's algorithm, right? So today we'll be discussing the Prim's algorithm, right? So let's get into the definition part first. So Prim's algorithm, let's see what the definition part say here, right? Prim's algorithm is a greedy algorithm, right? So it is used to find the minimum spanning tree, also MST of a connected, weighted, and undirected graph, right? So Prim's algorithm is a greedy algorithm used to find the minimum spanning tree of a connected, weighted, and undirected graph, right? It starts from an arbitrary node and repeatedly adds the smallest edge that connects a visited vertex to an unvisited vertex. Again, it starts from the arbitrary node, right? And repeatedly, it adds the smallest edge. Again, so we will be having the arbitrary node, and what it does actually, it repeatedly adds the smallest edge that connects the visited vertex to the unvisited vertex. So that's what it does. One thing, we'll be having the arbitrary node and the smallest edge that keeps on connecting the visited vertex to the unvisited vertex. That's what we have to remember here, right? Let's get into the definition part, man. See, the goal of the Prim's algorithm, explanation part, sorry. So the goal of the Prim's algorithm is to connect all the vertices with a minimum total edge weight without forming the cycles, right? The same thing. It's similar to the Kruskal's, right? At each step, what we'll do, we'll start from any vertex. You can start from any vertex, it doesn't matter. We'll pick the smallest edge connecting the current tree to the new vertex. This part is very important. So whatever we discussed now, this part is very important. So we'll pick the smallest edge, right? So we can start from any vertex, it doesn't matter. We will pick the smallest edge that is connecting the current tree to the new vertex. We will repeat until all the vertices are included in the tree. Again, we'll repeat until all the vertices are included in the tree, right? So it uses the priority queue, uh, so minimum heap basically, to efficiently get the smallest edge at each step. At each step we need the this one, right? Smallest edge. At, as I have said, that we will be picking the smallest edge connecting to the this one, connecting the current tree to the new vertex. So quite obviously we need the smallest edge at each step. In this case, we can directly make use of the minimum heap or the min priority queue, right? So yep. Now what will be the time complexity and the space complexity? So if you have listened to this, so this is not something that we are completely going in the detail. So we are going first thing, I'm explaining this one in the theoretical part, so that we'll implement the same thing while we write the algorithm in the form of code, right? So that's the reason we discuss the theoretical things first, right? So yeah. So now the time complexity and the space complexity. Let's discuss the complexities part. So what will be the time complexity of this particular algorithm? It's E log V, right? And the space complexity would lead to V plus E, right? So this is fine, man. Yeah. Now let's go with the example graph. So this graph, it's just for the example sake. So this is uh, undirected graph, right? Which consists of the value or the weights, basically. We call this one as weight. See here, A to B edge, for this edge we have the value 2. See this one, right? A to B we have 2. Then we have A to C, this one basically we have 3, right? So this is fine. A to B is fine, A to C is fine. Then A to D, we have this one directly. So this is 1 actually, right? So this is 1, right? So this is fine. Now we have to consider B to D. B to D is also 1. B to D we are considering, right? So B to D, it's 2 actually, right? So it's 2. 1 plus 1 will be, we have to go with 1 plus 1. So it will be 2. Basically C to D, so this one is 4 directly. So this one is 4. So basically what happened here is mistake. So this diagonal one, A to D is 1 and B to D is 2. B to D is 2, right? So don't get confused here, right? So it's not 1 plus 1, sorry. So this one here, it is showing 1 actually, this diagonal A to D. So this one is 1 and B to D is 2, right? So don't get confused here. So we are done with this part. Now we have the, this is one of the simple examples, right? So let's go with the this thing. Let's move on with the coding part actually. Algorithm, right? So first, as I've said, we'll be making use of the min priority queue or the min heap, right? So let's import the heap queue. So I'll just go with import heap queue. So this is fine. Now let's go with a prims algorithm function. So I'll just go with def prims algorithm. So this is also fine. Let me go with graph start. So this is fine. Yeah. Now within this, within the function prims algorithm, so we have the graph, nothing but the adjacency list, node, cost, and neighbor. So we have the starting vertex from the for the prims algorithm basically. Now let's go with the three this one, what do we call, initialization part. So we have to track the visited vertices as well. To track that one, let me go with the variable visited. So just go with the visited here. We give here set. We are just making use of the set, right? So there should be difference, right? So we shouldn't be visiting the same vertices. So we are just making use of the set here. So now let's go with a min heap here. So this one is min heap variable. Let me assign this one to the 0, comma, start. So this is fine. Now we have to store the total weight of the minimum spanning tree as well. For that one, I'll just make use of total cost here. So let me initialize this one to 0. Yep, fine. Now let's go with a while loop, man. So while of, let me give here min heap. So within this, we have to get the smallest weighted edge every time. So I'll just go with weight here. So this one weight. Mm, let me assign node to this one. Heap q. This is fine. Heap q. Dot. I'll just go with the heap pop. We have to pop as well. Yeah, we have to pop from the min heap, right? So let me pass min heap within the parenthesis. So we are just getting the smallest weighted edge every time. So as we had discussed in the explanation. Now, what if the node is visited already? So we have to skip, right, at that point of time. If node is visited, then we just have to give continue here. Right. So this one I forgot colon here. One thing about the Python here is if you know the this one language English, if you're good with English, you can just write the this one code pretty well. It's not this one. It's not a big deal to write the code if you know the English better. Right? So this is fine. Now, yeah, let's mark the node as visited. So I'll just go with here visited dot add of node. So this is also fine. Now let's add its edge weight to the total cost. So this one will be total cost equals total cost plus weight. Yep. Now let's do one thing. Let's explore all the adjacent adjustment. So let's go with a for loop here. So this is for next weight here. This is also fine. So this is neighbor and graph of node. Yep. So what if neighbor not an visited? Then what we need to do? I'll just go with a dot heap pop. We have to go with, I believe, right, heap push. So we have, sorry, I'll just go with the heap push here. What are the things that I need to pass here? Min heap along with the next weight here, this one, and the neighbor. This is fine. Yeah. So finally, what we need to return here, we have to return the total weights of the minimum spanning. Right. So just give me a second here. Yeah. Let me return this one, total cost basically. Yep. So we are done with the coding part. Now we are done with the coding part. Let me do one thing. Let me copy paste the. Let me get the example for this one from the Google. Just give me a second here. Let's go with the example usage for the interactive purpose, right? So just give me a second here. So this is the example basically. So this is nothing but the example graph that is represented as adjacency list, right? So you can just go through this one, and this MST cost, this one, this is nothing but we are just starting the prims algorithm from the vertex A. We can just consider any vertex, right? We can just initially consider any vertex as per the this one algorithm. So now finally we are just printing the minimum spanning tree just for the interactive purpose. Minimum spanning tree cost basically, right? So we have passed here mistake cost. This is fine. But so let me explain the algorithm before this one running the code actually, right? So I have just given here import EQ. So this is basically it is used to implement the minimum heap or the priority queue, right? So this is fine, I believe. I have explained this one multiple times. So this one visited, so here we are going with the visited set. This keeps track of the vertices already added to the minimum spanning tree. Then we are going with the min heap. Basically, we are starting with the edge of the weight 0 at the starting vertex. So that's what we are doing here. 0, see, start and 0 as I've given here. So 0 indicates that we are starting with an edge of weight 0 to the starting vertex, right? So then we have made use of the while loop here. While loop, what it does, so this runs until all the reachable nodes are this one processed, right? So now we are going with this one, what do we call heap queue of heap hop. So this one min heap. So whatever we are doing here, basically we are extracting the edge with the smallest weight. Again, primarily we are extracting the edge with the smallest weight. So if the node is already visited, it's skipped to avoid the cycles. This part, line number 48 and 49. If the node is already visited, we are skipping it to avoid the cycles. Next part is we are adding the edge weight to the MST total cost. What we are doing here, we are adding the edge weight to the MST total cost, right? So this is fine. For each neighbor, if not visited, we have to push its edge into the heap. Finally, we have returned the total MST cost, minimum spanning tree cost, right? So this is fine. So the output that we need to get here is 5, right? So I have checked this one. Let me explain you the same thing. So if I run the code, the output that I need to get here is 5. Why 5? I'll tell you. So this one, minimum spanning tree cost is 5. Why? So we are starting from the A. We are starting from the A. So the first point here is we are starting from the A as I've said, just said, right? So we are starting from the edge here somewhere. This one, 0 start. We are starting from the edge A. So we will pick the edge from A to D. From A to D, right? So you can just draw the graph here. So this one, A to D. So this one here, A to D, we have the value 1 actually. We have the value 1 or the weight 1. So this is fine. Uh, we are starting from A. We are picking the edge A to D. We are picking the edge A to D and the value is 1. Now, after this one, the second one, again, we will be starting from D now. We'll be starting from D now. So we'll pick the edge from D to B. D to B, right? So now we are having the this one D to B. The value will be 2 here, right? So the value will be 2 here, or the weight will be 2. Then we will be going from B basically. This time we'll be going from B. So now we'll pick the edge from A to C. Now we'll pick the edge from A to C. The value will be 3. Now we have picked the this one from A to C. The value will be A to C, C to A, C here, C and A. Right. So this one we have got the value or the weight 3. Right. So we have to sum up. So we are going with the minimum spanning tree cost. So this is the minimum that we have considered. Total we have to go with the this one total, right? So we will add this one. We'll sum up this one 1 plus 2 plus 3. So this one will be 1 plus 2, 2 plus 3, the total. So this is basically, 1 second. So yeah, here the value is 6. Sorry, the output that we need to get here is 6, not the 5 basically. So I said 5. So yeah, this one. Yeah, we have got 1. I have shown you the this one shortest path here, right? Uh, Shortest path from the edge basically, right? So I have directly showed you this one, right? Don't get confused here. 1 and 2 and 3. So overall we will get 6. I have shown you the edge as well here, right? So from which node also we have I have shown here. This is fine, right? So we have considered, or we have started from the vertex A. Now, this one, just keep this in mind as well. So let's start. Let's run the code. Let's see what output that we get here. So give me a second here. So let me give here Python by copy the file name dot py here. Hit enter. So we are getting minimum spanning tree cost 12, right? Just give me a second here. So what mistake I have done here is in the line number 48 is this has to be if node in visited, not if node is visited, right? So let me give clear screen and let me run this one again. Yeah, now we are getting the correct output. Basically, minimum spanning tree cost is 6, right? So yeah, this was the mistake, man. Yeah, we have got the correct output. I showed you the this one, right? How we got the output 6. Actually, this was the mistake. So one single word is instead of the n can give you plus 6 again, right? So nothing but that one. So I'm just kidding here. So this one, yeah. Now we have got the correct output, right? So this is it for the Prim's algorithm, right? So now we are done with the Prim's algorithm basically. Let's do one thing. Yeah, let me summarize whatever we have learned so far, right? So just try to remember these 3 to 4 points. So these are very important. So Prim's algorithm, what it does, it builds the minimum spanning tree by repeatedly picking the smallest edge that connects the current tree to the unvisited vertex, right? Again, so it builds the minimum spanning tree by repeatedly picking the smallest edge, right? So this is very important, that connects the current tree to an unvisited vertex, right? So in our case, we started from the A, smallest edge, if you remember, for the example that we considered, right? So the second point here is using the minimum heap. We have made use of the minimum heap itself, right? So using the minimum heap prevents unnecessary scanning of all the edges each time. So that is where this one minimum heap, this one plays a prominent role here, right? So using the minimum heap prevents unnecessary scanning of all the edges each time. Each vertex connecting edge is added exactly once, giving the correct minimal total cost. For this particular graph, the MST edges are A to D, D to B, and A to C. That is total, it is equivalent to the 6, right? So this one A to D, then D to B, this is also fine. Finally, A to C. So, which gave us the total 6 actually, right? So we saw this one, how we got this one 6. So I just explained before this one, right? So this is fine, man. Yeah, we are done with the Prim's algorithm, right? Next, basically, what shall we discuss next? Which algorithm shall we discuss next in the graph-based algorithm? Let's do one thing. Let's discuss the union find or the disjoint union set, right? So we have already made use of the union find itself for this, right? The path compression. So let's discuss union find or the disjoint union set, nothing but path compression algorithm next, right? So for now, this is it. Thanks for watching, guys.